Welcome back. We are happy to have Professor Baohua Fu from the Chinese Academy of Sciences. He will be talking about symplectic singularities arising from algebras of symmetric tensors. Yes, welcome.
Okay. Okay. First of all, I'd like to thank the organizers and the scientific committee for the invitation. It's my great pleasure to return BIMSA again after last year. It's a wonderful place. So I'm going to talk about some new constructions of symplectic singularities arising from algebras of symmetric tensors. So this is a joint work with Jie Liu from my institute. So let me start with the definition of symplectic singularities and the motivation for our work. So let me first start with the smooth case. Smooth case, what's the holomorphic symplectic manifolds? This is just a complex manifold, for example, M. For example, M is just a complex manifold of even dimensional, say dimension 2n, and then we require the existence of a two form. It's a holomorphic two form, which satisfies two conditions. First of all, it's declosed. If you take the exterior differential of this omega, it becomes a three form, and it vanishes everywhere. And then secondly, we require this two form is everywhere non-degenerate, which means if you take the highest weight product of this two form, then this gives you a section of this canonical bundle of this complex manifold, and we require this is everywhere non-zero. So this is does not vanish at any point. So in particular, this would imply this Km, this canonical bundle, should be trivial. In particular, this is a local color Biao, and also this gives you the trivialization of this canonical bundle. Huh? Yeah, it's even dimensional. Yeah. So this already implies always even dimensional. Oh no. It's a complex dimension 2n. Yeah. In my setting, yeah, everything is over C. So first, a trivial example is a 2n dimensional vector space, and then the two form. You just take the usual two form. Then you get this. This is the local model. In fact, it turns out every symplectic variety locally it looks like this, and then globally it can be quite different. And then the second example, for example, you take any smooth, any complex manifold X, and then you take the coordinate bundle, T star X, and then you have the projection to the space X pi. Using this, you can define a one form, which is called the Newell form, on this coordinate bundle, on the total space of this coordinate bundle, which is just given by, for example, you take a vector v on this tiny space upstairs, and then you can push forward using this pi. So d pi v gives a tangent vector on this x, and then you evaluate using this one form, using this this belongs to this tangent bundle, coordinate bundle. So you can evaluate on this tangent vector. You get this parallel. This gives you one form. And locally, if you take the coordinate, x is x1 to xn, then the coordinate bundle local coordinate is just x1 to xn, and then you add the y1 to yn. So locally, this one form looks like this. And in particular, if you take the d of this eta, then you get a two form, and locally it's just this form, because you take the d, then you get locally this form. So locally it's a symmetric form, and also it comes from d eta, so it's declosed. So this gives you this two form, and in particular this gives you a symmetric holomorphic symmetric variety, symmetric manifold, T star X. And this is just for smooth case. So the main goal of this talk is to try to mimic these constructions to singular case. For singular case, in fact, we have two sides. One is smooth part, one is singular part. On the smooth part, we have something called Calabi-Yau. Calabi-Yau, which means you have a holomorphic volume form. Otherwise, you have just a section of this canonical bundle, which is everywhere non-zero. And in particular, this would imply this Kx, this canonical bundle is trivial. And inside of Calabi-Yau, we have a small category of varieties of manifolds, which called holomorphic symmetric, just the existence of a symmetric structure, as I explained before. And then on the singular part, all these are smooth. And then we try to move this to singular part. For example, the analog of Calabi-Yau in the singular part, this is called the rational singularity. What's rational singularity? It's a normal variety with a local volume on this singular on the smooth part. And the condition is that whenever you take a resolution, this local volume form can be extended on the whole resolution. So this is give you rational singularity. This is one of the most simple singularities. And then inside rational singularity, Baohua introduced the notion of symmetric singularity. Just to mimic this analogy between Calabi-Yau and rational singularity. And then between holomorphic symmetric and symmetric singularity, is just defined in a similar way. Namely, we take a normal variety WO. O is just a singular point. And then we require the existence of a symmetric two form on the regular part. And then we have to put some condition on the extension. Namely, whenever you have a resolution of singularity, and then you can take the pullback of this two form. This pullback of this two form is only defined on the open part of the preimage of the regular part. And then we require this can be extended to a holomorphic two form on the whole variety. So in this case, this Y becomes smooth. And then we require this two form, just a global two form on the Y, on the whole of Y. But in many cases, this omega tilde is not necessarily non-degenerate. And whenever it's non-degenerate, then we say this is a symmetric resolution. So this is the definition of symmetric resolution. So if the extended two form is a symmetric structure, and then this implies this Y itself is a holomorphic symmetric manifold. And then we can easily show this symmetric resolution is equivalent to crimping resolution. So crimping resolution means this pi preserves the canonical bundle. So the canonical bundle downstairs, when you pull back, you get the canonical bundle upstairs. And then a result of Lamikawa, which says that which gives a simple way to say if it's symmetric or not. In fact, the symmetric singularity is just a rational Goldstein singularity plus the existence of a symmetric structure on the smooth part. So this give you a nice way to detect whether a singularity is symmetric or not. So let me give you some examples. For example, the baby example is C2n quotient by a finite group of SP2n. So SP2n is the set of automorphisms of this of linear transformations of C2n, which preserve their symmetric form. And then when you quotient, so on the smooth part, you have naturally a symmetric structure on the smooth part. And then C2n is smooth. So when you quotient a finite group, so this quotient has only rational Goldstein singularity. And then this shows by Lamikawa's result, this is a symmetric singularity. And of course, we can also easily check by just using the definition of symplectic singularity. And then the second class of examples is what we call the nilpotent orbit closures. In fact, the singularities of these varieties has been studied by Hynek and Panshiev in the 80s. In this case, this G is just a semi-simple Lie algebra. So you can take SLN or SPN and so on. And then you take any nilpotent element. And nilpotent means you have this linear map from G to G. So this is just a linear transformation of this Lie algebra. And then this is just take any element x, then you just take the Lie bracket with this V. So we just require this linear transformation is nilpotent. And nilpotent means if you compose itself by several times, it becomes identically zero. So it's basically you can think of this V just the nilpotent matrices. And then you take the G orbit of this nilpotent matrix or just this element. Then this give you a smooth variety. Because it's just a G orbit, so it's smooth. And in the classical case, it's just the conjugacy classes of nilpotent matrices. So it's, we can really write out with simply this object. And most importantly, this is not only smooth. It carries a symmetric structure. It's called a Costan Kirillov or Shukhyo symmetric structure. And this holds for any co-adjoint orbit, not only for just the nilpotent orbit. For any co-adjoint orbit, it has this symmetric form. And then this variety is not closed except V is zero. So in general, it's not closed. Then we can take the closure. But when you take the closure, then it becomes quite complicated. In general, it can be even non-normal. So in our case, we need to get the normalization of this closure. And then what Hynek and Panshiev they showed, if they take the normalization, then you get a symmetric variety. Namely, the singularities are rational constant, and also it has a symmetric form. And so the motivation of today is try to construct new constructions of symmetric singularities, just arising from these old constructions. So the first part, let me review some old constructions of symmetric singularities, starting with these moment maps. What are moment maps? So we still start with some complex manifold X, on which there exists a connected Lie group G acting on this X. And then you take any X, any point on this complex manifold. You can take the G orbit of this point, and then you naturally get a map from this Lie group to this orbital space. Just for any element in this Lie group, you just take the image is just the action of this element on this point. And this gives you a natural map. And then you take the tangent map of this very simple map. The tangent map and the space and the identity point. So this map will send this identity to just X itself. And then you get a tangent map from this Lie algebra of this G, and then to this tangent space of this X and this point. And now you take the dualization, dualize this linear map. This is just a linear map between two vector spaces. And then you get the coordinate space at this point to this dual of the Lie algebra. And then this gives you a canonical map. And then you can just put every point, and then you get a really very nice map from this coordinate bundle to this dual of the Lie algebra. So this is called a moment map. This is very natural and canonical way to define such a map. And then we take the closure. This map is not necessarily surjective. So we take the closure of the image denoted by mx. So this is just the image of this moment map. And of course, we have said before, this coordinate space, this has a holomorphic symmetric structure. And so one question is, what can we say about this mx? So maybe sometimes the mx can have a symmetric structure. So this is just one simple or basic question. So let me start with one example of this moment map. For example, if you take X is just the rational homogeneous space, just like a Pn or Grassmannian or partial flank varieties and so on. And then in this case, this moment map can be explicitly read out. Namely, this coordinate bundle of this G mod P, G mod P is rational homogeneous. So this coordinate bundle is also a homogeneous bundle over G mod P. Homogeneous bundle, so this is just given by a representation of this parabolic subgroup P. And the representation space is just the P perp. This the set of in the coordinate space which vanishes on this P. And then this moment map is given by you take a two point, this is G and this V in this P perp. And then this is actually just a joint action of this G on this V. So this gives you this this MP. MP is just an image closure. So this is the simplest moment map. And then Richardson in the 70s he showed in fact this moment map in this case is generically finite and projective. So generically finite means if you take a general point or take the general point in the image, then the pre-image just consists of several points. So it is generically finite. And furthermore, this image closure, this moment map image is just a nilpotent orbit closure. This nilpotent orbit closure is naturally associated to this parabolic subgroup P, so it's denoted by OP bar. And from this we can deduce that this moment map in this case is surjective. In general, it's not surjective, but because we have said this mu is projective, so its image is always surjective. And also, if you take the normalization of this closure, because it's a nilpotent orbit closure, it's not necessarily normal. But if you take the normalization, then this becomes the symmetric variety in the sense we have defined in the sense of bovine. So this gives you a really very nice situation where the moment map behaves quite well, and also the moment map image has a symmetric singularity. So the question is, what can we say in general for this moment map? For example, when this map is birational or generically finite or surjective or proper. Because if mu is birational, then you can try to descend the symmetric structure on the coordinate bundle to an open part on this mx. And then you can try to ask in this case whether we take the normalization of this moment map image, this will become the symmetric variety. And then if it's a symmetric variety, then we can also ask whether this becomes a symmetric resolution. So symmetric resolution means mu is birational and mu is also proper. So this is a very natural question associated with this moment map.
Is your G reduction for?
Oh no. This is for any G. Yeah. And so then for nilpotent orbit closures, in fact, I have shown in fact all symmetric resolutions of these nilpotent orbit closures are just given by moment maps. So there's nothing new. And for these questions, we have some answers. In fact, this is not original in our paper. It's just combinations of some old results by other people. So if you have a moment map mu, and firstly we show that mu is geometrically finite if and only if this G acts on this coordinate bundle of this X with an open orbit. So in particular, this G should be quite big, and also it acts on this coordinate bundle with an open orbit. And in this case, the G acts on this coordinate bundle with an open orbit, so this mu is G equivalent. And so this image has also an open orbit. And in particular, this shows this image should be the closure of a co-adjoint orbit. Of course, this G is not necessarily reductive, so it's hard to say whether this normalization of this MX is symmetric or not. And also, we show this mu is proper if and only if this X is rational homogeneous. And in this case, MX is just a nilpotent orbit closure. So this is completely decided, answered this question. And furthermore, by result of Klopp, if G is reductive, then we can show this mu is geometrically finite if and only if X is equal to G mod P. In this case, this MX is just a nilpotent orbit closure. And so from this sense, if G is reductive, then we cannot find the new examples of symmetric singularities. Because in this case, to give a symmetric structure on this MX, we need mu is at least geometrically finite to descend the symmetric structure downstairs. And then if G is reductive, then we only get nilpotent orbit closures. And then starting from this moment map, then we still can do something more using symmetric reduction. Symmetric reduction, which means you take the moment map, and then you take the pre-image of the 0 point, of the 0 of this one, and then you do the GIT quotient by this group G. Of course, this we need to assume G is reductive to do the GIT quotient. And then in most cases, so this candidates a symmetric structure on open subset. Of course, the main problem is to show this has only rational constant singularity. But this is quite tricky because this mu inverse 0, this is defined by some polynomials, and then it's not so easy to show it has rational singularity, for example. And then recently, these three people, Herbig, Schwarz, and Satan, they produced a lot of examples, and then they consider the case where X is just a G module, which means just X is just a linear vector space, a vector space where G acts on this vector space. And they produced many cases. They showed in most cases under some mild assumptions. This mu inverse 0 has rational singularity. And then you take the quotient, then the quotient has also rational singularity. And then they show in this case, this symmetric reduction is symmetric. So this gives you some examples of symmetric varieties. And then let me show you just one particular example, which is called a hypertoric variety. It's just one case of this symmetric reduction. So namely, we take just fix some m times n integer matrices. So this is A, and then we can define some group action of this torus, m-dimensional torus, acting on the coordinate bundle of this vector space C big N. This is just given by the following formula, and using this entrance of this matrix A, just given by this formula. So you just act on this column each Zi is actually on this column, and on this second part, Wj is on the coordinate bundle. So the action is on the inverse. So you take the minus Aij on this Wj, and this give you this a group action on this Cn, and then you get this moment map. And this moment map is very explicit. So you can take this Z and Wj just maps to this by this quadratic polynomials. And then the hypertoric variety, you just take the preimage of 0 and quotient by the action of this torus. So this is called YA0. So this is one example of symmetric reductions, and this is hypertoric. And then if we assume under some mild assumption, for example, assume this A, so we have this big matrix A, big matrix A, so we can construct this linear map between the integer vector space Zn to Zm. We assume this is surjective. And furthermore, we assume existence of some other integer matrix B, which makes this short sequence exact. And in this case, and also we assume this B has no zero or being 0. And then in this case, Bellamy showed in 23 in last year that this YA0 is a symmetric variety. So they give you another symmetric variety. And in fact, from this, he deduced that the Coulomb branches are symmetric varieties. Okay, so this is the first part on the symmetric singularities. And then in my title, we have two parts. So the second part is on the algebras of symmetric tensors. So what are algebras of symmetric tensors? So I take X is a smooth projective variety, and then I consider all symmetric product of the tangent bundle, and then take the global section of this symmetric product of tangent bundle. I put all together. Of course, this give you a Z-granted algebra because this same P. So you have a natural product from same P times same Q to same P plus Q. So you get an algebra structure on this X. So this is called algebra of symmetric tensors. And in other words, we can also put this on this projectivized tangent bundle, because if you push forward, you have this because you have always this PTX 2x, you have this pi, and then on this OP, this tautological bundle OPT, and then if you push forward, then pi star this OPTX P, this becomes to a symmetric product of this TX. So from this, so you deduce that that you can either work on this base of X or on the base of this projectivized tangent bundle. And then another way to say this is just the coordinate range of this coordinate bundle of this X. And the definition looks quite simple, but in fact this algebra is quite intricate. There are a lot of things we don't know much. So a baby example, if you take an abelian variety, if you take an abelian variety, then the tangent bundle is trivial. It's trivial, so Tx is just X times Cn. As X has a low global section, so you just have Cn. The global section just comes from Cn. So Cn, so the coordinate range of Cn is a polynomial range of n variables. So you get this one, and this is graded just by degree of the polynomials. So this is just a baby example. And this algebra are extensively studied by Baohua and Jie Liu in last year. You find that they proved that in many cases this algebra is trivial. There's nothing to say. For example, if you take x is color Biao, color Biao in a strict sense, which means we not only require this C1 is 0, this means just the canonical boundary is trivial, and also we require this pi 1, this fundamental group is trivial, so it's a strict color Biao. Or if x is of general type, yeah.
For example, if I take x to be P1, and then the tangent boundary is of course O2, and the projectization is again P1, and pi is identity. But then the formula then says that O1 is O1 equals O2.
Yeah, but in this case, pi is just isomorphism.
Yeah, pi is just identity. So then,
yeah.
But then the formula wrote becomes O1 equals O2.
Oh yeah, maybe we need okay, we need a dimension is at least 1, at least 2. X. Yeah, otherwise it's trivial. Yeah, there's no fiber comes up.
Okay, maybe I can ask you later.
Yeah, for curve case, everything is trivial. Yeah. And then they also show for hypersurfaces of degree of dimension at least 2 or degree at least 3. And in all these cases, this algebra are trivial, which means all the higher order symmetric tensors vanishes. So there's no non-trivial one. And the most interesting part of this work is that they have an upper bound for this core dimension of this algebra. So the core dimension is bounded by the dimension of x minus this quadratic dimension with this x. And also with equality, if and only if x is just a finite quotient of a product of an abelian variety and something of general type. And in particular, you say if this x has a dimension bigger than the dimension of x, then the quadratic dimension should be minus infinity. So in fact, this is the only case we were interested. Yeah. This is a question of Baohua. So this algebra is finally generated or not? Yeah.
You still can talk about two dimensions, like maximal lenses.
Yeah. And then even for this case, they computed many examples, and then this question is still out of reach. We don't know. Yeah. And then we come back again to this my first example of this rational homogeneous space X. And then before we have this moment map. So moment map, the image becomes a nilpotent object closure in this Lie algebra. This is geometrically finite by Richardson result. And then you can take a Stein factorization of this morphism of this moment map. Then you get a mu hat. This becomes a symmetric resolution. This becomes birational, and then this becomes just a finite map. So this give you a finite cover of this nilpotent orbit closure. And then if you compute this algebra of symmetric tensors, and then you find out that this algebra of symmetric tensors is just becomes the coordinated range of this cover of this nilpotent orbit closure cover. And so in particular, I'll just give you the explicit way to say this symmetric algebra of symmetric tensors in this case is just the coordinated range of this nilpotent orbit cover. And now we set this Zx is just a spectrum of this Sx. But it's just a scheme. It's not necessarily a variety because we don't know if Sx is finitely generated or not. So just a normal scheme. And then we get a natural morphism from this coordinate bundle to this Zx, because this is just Zx is given by the global section of this coordinate bundle. So you get a natural dominant map. So this is a map quite similar to moment map. And then we can ask a similar way, what happens for this map compared to a moment map. So similarly, for example, we can ask, when is this map constant? Constant means just the algebra of symmetric tensors just C, or when it is surjective, or proper, or bidirectional. And when it's bidirectional, then we can ask, when is this image becomes symplectic variety? And if it's a symplectic variety, then we can ask, when this is a symplectic resolution. And then we have some examples. For example, if x is G mod P, then this algebra of symmetric tensors is just given by the coordinate range of this nilpotent orbit cover. And then this Cx is just given by this OP hat. And then phi x is a symmetric resolution. So in this case, so all these are answered, and we have also examples where this happens. And then in fact, a conjecture of Campana and Peter Net, in fact, they have a stronger conjecture, and this is just a part of their conjecture, just a special case of the conjecture, which says that if this natural map is a symmetric resolution, and then x must be G mod P, and then we have nothing new. So this conjecture will completely resolve the last question. And so our main goal is try to answer the first and second question in this paper, part of this. And also this conjecture is known up to dimension 5. Namely, if this Zx has a dimension up to 10, then this is proved. But the proof is quite a case-by-case proof. So it's quite difficult to extend to higher dimension. So let me come to the main theorem. So before giving the main theorem, so I need to introduce some notion. So we have said this Sx is the algebra of symmetric tensors. So it's Z-grounded. Z-grounded, and then maybe I write this Sx. So Sx is just a direct sum. For this one, so you can say it's graded. So each piece, this is a degree P piece. And then we say this Z-grounded algebra is reduced if there exists some algebraically independent homogeneous elements Z1 to ZL, such that the greatest common divisor of these degrees just 1. So for example, if Sx is generated by degree 2, then you cannot get it's not reduced. However, for example, if you have some group acting on this X, or X has a continuous automorphism group, then Sx is reduced. Because in this case, you say this first part of P equal to 1, then you get this H0 of XTX. So if this is non-zero, so you can just already take something of degree 1, so it's reduced. So in fact, this is the main case we will apply to our situation. And also we need two notions. First of all, we say this tangent bundle is big. Usually big we defined by divisors. So this tangent bundle is big. if this tautological bundle on this projective divisor, the tiny space, is a big divisor on this PTX. So big divisor means that you can write this is the sum of one ample divisor plus something effective. Otherwise, we can also define this big by saying it has a lot of sections on this global this tautological bundle. So if you take this OPTXP, and then this global section increase just at the rate of the dimension, or the polynomial of degree of the dimension. And also we say this varieties of final type. Final variety, which means just minus k is ample, but the final type is a weaker condition, which means you can find some effective Q divisor, such that this minus ky plus delta is ample. This is first, and then the second is this y delta is KLT, so it has only KLT singularities. KLT means Karl-Marta log terminal. So, for example, if y is a final variety, final manifold, then this holds. You can just take a delta is 0, and then y is already KLT. And so the first main theorem reads as follows. So you take x is smooth projective variety, and then you have this natural map, this phi x from the coordinate bundle to this zx. And then firstly, we show this phi x is birational if and only if there are two conditions. First of all, if and only if this tx is big. Tx is big, which means if you take the projectivized tangent bundle, then you have this tautological bundle. This tautological bundle is big. And then secondly, we require this Sx is reduced. This algebra of symmetric tensors is reduced. In fact, the first part, Tx is big, which means this map is geometrically finite. And then this Sx is reduced, which means this is birational. So general point, it has only just one pre-image. And then we show if phi x is birational, then Zx is symmetric variety if and only if it is projectivized the tangent bundle is of final type. Final type means you can find some effective divisor, such as the minus k plus this delta is ample, and also this PTX with delta is KLT. So this gives an answer to the previous case. So if you go further, so we need to understand which varieties have big tangent bundle. And in fact, this has been studied previously by some people. In fact, there are some examples where which has a big tangent bundle. For example, if you take a smooth projective toric variety. So toric variety, this has been proved by this Xiao from Taiwan in 2015. And then a second class of examples given by Jie Liu last year. So we say that if you have any smooth projective whole spherical variety, what means the whole spherical? Which means you have a G action on this variety. This G action has an open orbit. This open orbit looks like just a torus bundle over rational homogeneous space. For example, if you just take a toric variety, toric variety is whole spherical, because toric variety is just you take this G mod P just one point, and then you just give a torus bundle. Because toric variety you have already a big open torus, so you just take a trivial fibrilation, and then toric variety are whole spherical. But whole spherical is much larger. You have many such examples, and then this gives you a bigger tangent bundle. And then third one is just one particular example. Just take the Grossmanian 2-5. So this is 6-dimensional homogeneous variety. You take a codimension 3 linear section, and take a general one, then you get a smooth variety. This is called a quantic Delpezzo threefold. And this has been shown by Horan, Liu, and Sao Feng in the paper. This threefold has a big tangent boundary. And then a natural question regarding to our main theorem is whether for these three kind of examples, can this Zx has symmetric variety, symmetric singularity, because for this case we already have this Tx is big. In fact, this is the case. In fact, for these three cases, we show that Zx is symmetric variety, either for smooth projective toric variety, or a smooth whole spherical variety with small boundary, or this V5. V5 is just this one, this V5. So what's the difference between these varieties and in our main theorem? In our main theorem, the only difference is this whole spherical case. We add some condition. So we need the boundary is small. I mean, which means the boundary is at least has a codimension at least 2. So this is the main difference. And we expect even without this condition, this is also true, but we cannot prove this. So the corollary, in fact, for this variety, we obtain that the projective by the tangent bundle is of phenotype. In particular, these are more regime space. In fact, this even for toric variety, this seems to be a new result. So even for toric variety, before we don't know it's a phenotype, because phenotype is it's not so easy to check. You need to find the divisor, such as the minus k plus this divisor is ample, and also x with this divisor becomes KLT. And so next question is for this main theorem, for this theorem, so we get 3 classes of new examples or of some new construction of these symmetric varieties. So what are these varieties? What are they? Are they really new examples? And how about the symmetric resolution for these varieties? So what are these symmetric varieties? So we have 3 types. So the first type is toric variety. So you take a smooth projective toric variety. And for each toric variety, you have this toric fan. Toric fan, then this sigma 1 means just, so you take a fan structure. This is just given by this one-dimensional rays, the set of one-dimensional rays. And I use just, I would say, this toric variety, this fan, one-dimensional ray corresponds to divisors in this toric variety. And so from this, you get a natural map from this divisor to beta group. And of course, every line boundary in the beta group can be generated by torus invariant divisor. So this gives you a surjective map. And then the kernel is given by some lattice. And then this gives you a map. This is called an integer matrix A. Of course, when you say this one, then you remember we have this hypertoric varieties. Hypertoric variety, maybe I just recall this hypertoric variety. Just you start with some integer matrices A, and then you can construct some torus action on this linear space, and then you take the symmetric reduction. You get a hypertoric variety. And this is YA0. And then under some mild assumption, in particular this first, this A, this linear map given by A is surjective, and also another on this kernel B. And then let me show this is a symmetric variety. And in fact, the toric case is just one of these examples. So in fact, in our case, for X is smooth particle toric, then we show our constructed variety ZX. In fact, is just a hypertoric variety, YA0. And from this, then we can use a recent result of Namikawa. Namikawa, in fact, he studied this hypertoric variety with symmetric resolutions. In fact, from this, we deduce that this ZX admits a symmetric resolution if and only if A is unimodular. Unimodular, which means if you take any square submatrix of this A, its determinant either 0 or 1 or -1. So just the unimodular. But this A, so another question is how to interpret this condition geometrically. Because this A, we say this A is just given by this fan structure to this beta group. And then, we still don't have an idea how to interpret this. Just give some geometrical interpretation of this condition. So this is the first example. And then let me do one particular case. You take a Pn. Pn is toric. And then you block one point, and this Pn. And then I would like to compute this Zx. What's Zx? So of course this is Zpn. Zpn is just given by this before this T star Pn to this Zpn. As Pn is homogeneous, so this is just a nilpotent orbit closure. So this nilpotent orbit closure is just the all mean. All mean is just the traceless matrices with rank and most one. So this is just a conjugate classes of nilpotent matrix. And then what's this Zx? If we can describe it as follows. So this is just given by trace B equal to 0. There's no trace, and also we require this rank of B prime is at most one. So what's a B prime? B prime. What's the difference? Is just you put the last entry by minus its square. So this is the only difference. So it looks quite strange. This variety. And then as before we have this blow up. So we have this Pn. X is a blow up Pn to this X to this Pn, and then you have this exceptional divisor E. And then outside of the exceptional divisor, this is just a Pn minus 0 this point, and then you consider this coordinate bundle. So the first part of these are the same because the base is the same, and then this is different, and then this is the divisor inside this one, and this is a coordinate and this 2. So of course we need to require this n and this 2. So in this case, so we give a natural map from this algebra of symmetric tensors on this X to this Pn, and in particular, this gives you a map from this Zpn to this Zx, and this map is we can really explain right out. This is just take this matrices n plus 1 by n plus 1 matrices, and then you just what we change is just the last row. We just multiply by this minus of the last entry, and this will give you this map. And from this map, then we can show this Zx is singular along codimension 2 locus as the genetic singularities are A1. A1 singularities, then you can just blow up. Then you can resolve the singularities along this A1, along this S. And then blow up, then we still have isolated singularities, which is of type this all mean. And this all mean just this one. This is all mean, and the symmetric resolution is just given by coordinate bundle of this Pn. And then compose with this symmetric resolution of this all meme. Then we finally get a symmetric resolution to this Zx. And the fiber has two PN, which is intersecting at one point. And then you can perform two Mukai flops. One put up this one, another Mukai flop along this one. So you finally get three different symmetric resolutions on this Zx. So this gives you one example. And then the second kind of example is horse-vertical varieties. But we cannot do for all horse-vertical varieties. But we just do this the case of big number one, non-homogeneous, because the homogeneous case is trivial. And this has been classified by Baohua Fu. And in this case, the automorphism group is non-reductive. Non-reductive, so we still can do this. This is a natural map, and this is a moment map. A moment map with respect to this non-reductive group, and then we can take the m hat. M hat is not a staff factorization because this is not a necessarily projective. So we can just take the normalization of this mx inside the function field of this coordinate bundle. We get such a map. And then for this, what we can show is that this mu is generically finite. This mu is a moment map. So the moment map is generically finite, which means the group acting on this coordinate bundle with an open orbit. And also this Zx is bidirectional to this normalization of this moment map image in the function field of Tx. So this gives you a way to relate this new example to this moment map. And the last one is quintuple del Pedro threefold V5. In this case, we show this Zx is a six-dimensional symmetric variety. And in this case, we can really explicitly construct the Q factorial terminalization of this Zx. And then we deduce that this is not smooth. And we deduce that this Zx does not admit any symmetric resolution. So I think my time is up. So thank you all for the attention.
Thank you, Professor Fu, for the talk. Any questions?
So for the final type, and do you know the Picard number of those final varieties?
Sorry.
You mentioned some funnels they are also more dream spaces.
Yeah.
I just wonder whether you know their explicit Picard numbers.
Yeah, Picard number, that depends. Yeah, it can be. Yeah, for example, in this case, we only consider Picard number one, but in general case, it can be arbitrary. Yeah, you have many. You have all examples for all Picard number. In this case, why we consider only Picard number one case? Because in general, we need to require this has a small boundary. So small boundary, so which means so if you have x and then you have this G more h, so this is the open Horsch-Verg, and then you have this torch bundle over this this G more p. And a small boundary means a small boundary. Small boundary means just the codimension of this x minus G more h is at least 2. So the Picard group of this one, or Picard number of this one is just the Picard number of this one. Picard number of this one is just the Picard number of this one. But this G more p you can be arbitrary.
Any other questions?
I mean, here you only consider the smooth projective case. Can you extend this to the affine case, for example?
Oh yeah. If for example you consider all this one, so this will not change if you just change of codomain 2 underneath 2. Yeah, but if you take a affine case, then it's not finite dimensional.
Yeah, of course.
Yeah. So then I don't know how to how to handle this. Yeah, if it's not a finite dimensional case.
But you can always come back to part, but then you get something
Yeah.
singular. Right?
Yeah.
Okay.
Okay.
Also,
in fact, we do many manipulations. We replace this by some outside code main too. Then you can do many surgery.
I see. And also you consider this hollow spherical one, but there are other spherical, right?
Yeah. Spherical. No. We don't know how to do this.
Okay.
Yeah. We really need this structure. Yeah. This is torsion bound over this one.
Okay. And final question is that you said this big divide.
Big. Yeah.
There's some notion of big is equivalent to the moment map is finite.
Yeah.
Generically finite. Is it true?
Yeah. The moment map is you mean is projective or?
Yeah, I think the next slide.
Yeah. This is just finite. No moment. Yeah. This one.
It's so it's also equal. I mean, mu is generically finite. Is also equivalent to the.
Yeah. We don't know. Yeah. If we remove G reductive, then we don't know. Yeah. If G is non-reductive, so we have already one example. This Horace-Berg variety. This Horace-Berg variety is non-reductive, but it's still generically finite.
Okay.
Yeah. This one. In this case, pick number one, Horace-Berg. Then this automorphic group is non-reductive, but still, this moment map is generically finite.
I see. Thank you.
Okay.
Any other questions or comments? If not, let's thank Professor Fu for the interesting talk.
Okay. Thank you.